to solve this equation by using Fourier transforms. It's a quite simple algebraic form like this. And to define Fourier component of electromagnetic potential, we have to determine magnetization My depending on K via this Fourier transformation, which depends exact solution of double sign Gordon model theory. This one. This phi angle describes magnetic order corresponding to 1s or 2s configurations. If we perform this task, we get My, then recover a K, then substitute to the expression for magnetic phase shift. In the explicit form, convenient for calculation, it applies the following form. So this is a program how to determine analytically magnetic phase shift. I will say that this task is rather routinious. It requires some knowledge, of technical details, Fourier transformations of elliptic Jacobi functions, and eventually, we may obtain compact analytical results for each of the mentioned above phases. For example, for 1s, we get this simple expression. It contains Jacobi amplitude function. Some parameters appear here, like b. It comes from exact solution of double sign Gordon model. I don't give here the explicit expression because it's rather complicated. But if someone get interested, details may be found in our original paper. The same procedure may be performed for another phases of the double sign Gordon model 1s bar. This is totally the same as 1s, but the sign B2 is positive one. And we get this expression. Now the issue is how to extract physical information if we have magnetic phase shift in hand. Here we have to recognize 3 different techniques for Lorentz microscopy. If we operate directly by magnetic phase shift, we deal with electron holography, but this method is almost not used to analyze magnetic structure. Another technique is known as Foucault technique. It uses first derivative of magnetic phase. But this method is convenient only for magnetic inhomogeneities of big scale, where size is of order some micrometers. But for very tiny spin modulation, it's almost inappropriate because all information is lost. To analyze magnetic arrangement at the nanoscale, it's convenient to use so-called Fresnel technique. It's operated by the second derivative of the magnetic phase shift. This expression has been derived in the original paper of one of our co-authors, Stephen McVitie, more than 20 years ago. And it contains some technical parameters here, delta F, this is defocusing distance, and lambda, this is wavelength of incident electron peak. So these are pure apparatus parameters, so only second derivative of phi carry information about physical behavior of the system. To find out how tensile deformations affects the profile of intensity of Fresnel micrography, we perform scans of the phase diagram along the directions shown here by red arrows 1, 2, 3 to investigate 1S phase. And the same procedure were done for 2S phase. Here scans are shown by yellow arrows. Our strategy is following. We fix a B2 parameter which responds for tensile deformation. We fix stress that affect the sample. And then start to vary external magnetic field. We increase V1 parameter and we trace how profile of intensity varies with the magnetic field. So we see that profiles of the intensities vary drastically depending on the magnetic field and the stress. Here we see that changing V2, how to say, causes very noticeable rebuilding of the profiles. The same principle retains for 2S phase. Here, profiles are totally different from that of shown above here. So we may conclude that Fresnel technique, Lorentz microscopy technique, gives us very precise tool to investigate deformations of the magnetic structure. To verify these theoretical findings, some experiments were performed. It was carried out in Glasgow University by Gary Patterson, Stevie McVitie, and Yoshi Tagawa. Because I am a theoretician, I just briefly explain the main idea of the experiment without any technical details. First of all, a thin slab of chrome niobium sulfur 2 were cut from the bulk material in such a way that C axis lie within the plate of this slab. Then a special cradle made of silicium were cut is the form of horseshoe, and our sample was stretched out between the legs of this horseshoe. Then, when we start to hit this cradle, silicium cradle, the legs start to diverge, and this causes tensile deformations like shown in our cartoon picture. Then we perform experiment on this sample subjected to the tensile deformations. And to start, I noticed that indeed Lorentz microgram shows that additional intensity seen as a thin white bands appear like this. If we analyze profiles of intensity, we may notice also appearance of additional peaks shown here by black arrows. Very interesting. It's not directly related with our topic, but interesting that sample split it into the domain of different chirality, and this boundary between the grains of different chirality is distantly seen in the experiment, like inversion of profile. These peaks turn over in comparison with those shown at the left. This is very curious fact, but it's agree with the theoretical description. Then we start to compare this profile with those obtained in previously when we built theoretical pictures. And we see the most probable candidate to explain what we see is the diagram shown here. See. We may compare experimental profiles with the theoretical one and see very nice agreement. very strikingly. And from this comparison, we notice that most evident coincidence is happens at the intermediate magnetic field. But in principle, it could overrule the field scale, field axis. So we may conclude that in this experiment we face with so-called oneness phase. And now a short history. This phase was firstly predicted by Soviet physicists Golovko and Sannikov from Moscow Institute of Crystallography in 1982, when they analyzed with aid of the double sign Gordon phases in liquid crystals. Independently, the same analysis was carried out by Japanese theoretician Iwabuchi, and he published a paper in 1983, but it totally focused on the peculiarities of this 1S phase. So we took many mathematical details from this paper, so we give priority to him that he was first to predict the appearance of this phase. And now I conclude my talk. It will be very short, that we may conclude that double sign Gordon model is relevant for description of the deformation of magnetic solid lattice subjected to tensile deformation. If somebody will get interested, please see technical details in our paper. And thank you for your attention. Okay.
You are studying the deformations in the chiral soliton lattice. These deformations, which is the percentage? How much you deformate?
Each of spiral.
Yes.
Each of spiral plus this. At the moment, I cannot say details. Because I remember there is special equation appears like equation of state. Big, of course, have to rederive each of the spiral, but they look different for each of the phase. For example, I can share this. For example, some expression like this one, they involve both constant B2, B1, contain some elliptical integrals, and from this equation of state we have to derive few features of the spiral. But in our investigation, we didn't focus on this because it's believed that this problem has been solved. Our theory is constructed. We didn't compare directly with features of the spiral.